Hi, we finished this chapter talking about convex functions. So we said that a function f is convex on an interval I if for all x1, x2 in I and for all t between 0 and 1 we have the image of 1 minus tx1 plus tx2 less or equal than 1 minus t times f of x1 plus t times f of x2. What does this mean? Let's say you have a function like this one. And we take a point x1 in here and a point x2 in here. So, first you should know that 1 minus tx1 plus tx2 is a point that is between x1 and x2. Because if t belongs to 0, 1, then for example t is equal to half. So 1 minus half x1, it's half x1, plus half x2, it's the middle point of x1, x2. If t is equal to 0, then 1 minus t x1 plus t x2 will be equal to x1. So it's the first point. If t is equal to 1, then this in here will be equal to x2, so the last point. So again, if t equals to 0 or 1, you will have the boundaries, and if t is between 0 and 1, you will have all the points between x1 and x2. So when I say f of 1 minus tx1 plus tx2, I am pointing out the images of all the points between x1 and x2. So any point you choose between x1 and x2, its image will be its image on f. Okay, let's take this point. Its image on f will be less or equal than 1 minus t f of x1 plus t f of x2. F of x1 is in here. This is f of x1. F of x2 is in here. Okay, so 1 minus t f of x1 plus t f of x2 is a point between f of x1 and f of x2 as well, for the same reasons as before. But more interestingly, it's exactly this point. So if you join these 2 points and you prolongate this one, it's exactly this point. So this point is 1 minus t f of x1 plus t f of x2. Why? Because of the ratios. So I mean, if this is the point that is 1 minus t x1 plus t x2, so t is defining the ratio that says that it's defining the ratio between this part and this part, let's say, and according to Thales theorem, so we have this divided by this equals to this part divided by this part, which is equal as well to this part divided by this part. So t will define also the same ratio in here. So 1 minus t f of x plus t f f of x1, sorry, plus t f of x2 will be this point in here. So this inequality, it's saying that if you choose a point in here, its image on f will be less than its image on the straight line joining x1 f of x1 and x2 f of x2. In this case, the function is convex. So if any function that is turning like this is convex, even if it's not decreasing then increasing, it can be only increasing, like let's say exponential x. And any function that is making this shape, it doesn't satisfy this property. It's said to be concave. So also we can say that this one is convex up and this one is convex down. So back to the course, we say that if let I be an interval of R, f defined from I into R, we say that f is convex if and only if for all x1, x2 and I, for all t between 0 and 1, f of 1 minus t x1 plus t x2 is less or equal than 1 minus t f of x1 plus t f of x2. Equivalently, we can write it in another way, saying that for all x1, x2 in I, for all alpha beta in R plus, such that alpha plus beta is equal to 1. So it's like saying we have t and 1 minus t, it's the same thing. We have the same inequality. And we say that f is concave if minus f is convex, which translates into f of 1 minus t x1 plus t x2 is greater than 1 minus t f of x1 plus t f of x2. So we can prove also a more general formula saying that if f is convex, then you can take not only 2 points x1 and x2, but you can take n points and n coefficients lambda 1 to lambda n with sum of lambda k being equal to 1. Then you will have f of lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 etc. until lambda n xn less or equal than lambda 1 f of x1 plus lambda 2 f of x2 plus lambda 3 f of x3 etc. until lambda n f of xn. And this can be proven by induction using the initial formula of that convexity. Of course, the proof in here is not required for you. So according to our understanding of the definition, we can also conclude these two results. First, if f is differentiable, then f is convex if and only if f prime is increasing. And you can notice that taking a convex function like this one, f prime is increasing because first your slope was like this, and then the slope is like this, and then the slope is like this, etc. So the slope is increasing. So having f convex, it means that f prime should be increasing. And also if f prime is increasing, then f is convex. Be careful, this is only true if f is differentiable. It means that you can have functions that are convex without being differentiable. So we have functions that are convex and that satisfy the initial definition of the convexity without satisfying this theorem if they were not differentiable. Also, you can prove that if f is twice differentiable, then f double prime should be positive. Again, this is only true when f is twice differentiable. So if f is not twice differentiable, it can be convex without having this property. But if it's twice differentiable, then of course you can prove the convexity using f double prime greater or equal to 0, or the converse, saying that if f is convex, then the second derivative is greater or equal to 0. You can take the following examples, like e of x, I drew it before, x2 also is convex, ln of 1 plus ex, all these functions are convex, they are twice differentiable, so you can calculate the second derivatives and you can find that they are positive because the second derivative of ex is ex, it's positive. The second derivative of x2 is equal to 2, this is g double prime, and the second derivative of ln of 1 plus ex, also you can do it, it's in fact it's ex over 1 plus ex, the first derivative, and then the second derivative will be something positive. So these functions are convex functions.